A bit more time to get into, starting to introduce the idea of skin. And to do that, I'm going to start by showing you a very simple definition that's called box morph. And what it does is it takes a geometry that you've modeled and it will warp it to fit. This is the part that's extremely similar to what you did with Revit. But it'll morph it to fit into the panel that you've subdivided on a surface in 3 dimensions, not just 2. So when we did saddle patterning, that was a 2-dimensional geometry that fit into the panel. So now we're dealing with the actual 3-dimensional plane. So to get us going here, slide this down a little bit because we're going to take a detour and start building another script above it. And also, you can turn off, well, you pretty much turn off everything, but definitely turn off everything at the bottom. And turn on loft. So that deconstruct brep that we had on loft, that's important now. But if you've got a curved surface, you're only going to have one output here under faces, and that's okay. I'll show you both ways of doing it. Well, actually, yeah, I'll show you both. Well, I'll start with one. So I'm going to ask you guys to please change your degree to 1. So change your degree to 1 so that we're working on one face for now. That won't always be the case, but we're going to start here. So I don't need this panel anymore, but I do want these surfaces, right, the faces. So I need to do a list item because I'm only going to do my box morph on one face, right? So I'm trying to keep it pretty close to what you were doing in Revit, okay? So it's comparable. But so box morph on one face looks like this. So sets, list item. Plug the faces into the list and do a 0 to 3 slider. And this is going to help us pick which face we're going to use. So for me, I want this outside face here. You can pick whichever one you want. I'm going to work on this.
What's the deconstruct brep plugged into?
That is plugged into the original loft skin. That's plugged into, oh, where is it? That is under surface analysis. Okay, so we've got the surface that we want to create a panel on, and we need to subdivide it. So the subdivide now is going to be a little different because rather than subdividing and using isotrim, we're going to start to rebuild the subdivided domain in 3 dimensions. So let's start with the actual subdivide itself, and that part is the same. So you go to Math, Domain, and we do Divide Domain Squared. Plug that in. You could start with 10 by 10 right now, but I'm going to put sliders on for 0 to 100.
How many?
0 to 100.
No, how many sliders? 2 sliders?
Yes. Yeah, 1 for the U and 1 for the V. I'm going to start off here with 25, 25. Well, 25 and 10. So then to create a three-dimensional domain, we go under Surface, Utility. Sorry, where was that again? Might be under Transform. Yeah, there it is. Sorry. It's under Transform, Morph, and Surface Box. So now we're getting into real morphological functions. So this one actually is similar to isotrim. It's going to ask you for the surface that you're dividing. It's going to ask you for the domain input. And then it asks you for something else. It asks you for the height of the surface box. And that's very significant. So when I plug the surface in, and then I plug the domain in, it comes with its standard height, which is 1. And if you look at it, this is what it's doing. It's creating a 1 foot thick panel across the surface. So let me put a slider on that. 0 to 10. Plug that into the H. And now, as I move it out, you'll really begin to see how a three-dimensional panel is being mapped. You're going the other way?
Yeah, it's going inside.
Just make it a negative.
Okay.
Yeah. So that's another thing that I, for some reason, just haven't been able to figure out why it chooses that particular normal to be on that side of the surface. You could use reverse as well, if you want.
Just type it in.
Yeah. So yeah, if any of you guys have it going on the opposite side that you don't want, just use a negative height number, and it'll go to the outside. All right, so now that we've got our box, let's start looking at morphing a tile into it. But first, we need to actually create the tile. So I will say this. When you create a tile, and there's a bit more that I want to learn before the end of the class here in terms of creating geometry through a morphed domain, but when you create a tile, it will map to the entire extent of that tile. So what does that mean? It means if I create something that's an odd form, it's going to stretch it so that it fills up the entire U and the entire V length of the tile. And well, it looks like this. Okay, so let's do something really simple to start. We have to model this in Grasshopper. Well, we don't have to. We could do it, we have to model this in Rhino to just make it easy. And you could do this in Grasshopper too, but we're gonna start easy. So I'd like you to create a rectangle, and we're gonna place it here. Just place it anywhere in the workspace and make it 10 by 10. So I'm going to say at 10 feet by 10 feet. And for this pattern, I'm going to start cutting a few things out. So I'm going to do circles on the corners. So pick a circle distance, but don't cross the midpoint. Make it a little bit shallower than the midpoint. And then copy it to all four corners. Then you can use trim. So type in trim and hit enter if you aren't familiar with it. Select the curves, hit enter, and then start cutting it out so that the remainder is an inverse rounded corner. And inside of this curve, I want you to make another closed form. It could be a circle, but you could also, make it a pattern if you want so that you can see orientation. What I'm going to do is I'm going to make a box move it into the space a little bit, and then make another one just a little bit above. So this will help you guys understand the relationship of the geometry once we map it in, because the X and Y direction does matter. Okay, so after that, it doesn't really matter how thick you make this, but we're going to do an extrude curve. Well, it doesn't matter how thick you make it now, but I'm going to make it extruded 1 feet. 1 foot. Thank you. It's brown feet. Lord of the Rings, anyone? No?
I haven't seen it in forever.
All right. So this will be our tile, at least for right now. Let's start to actually create the box morph part. So there are 2 parts to the actual box morph. And forgive me, I don't use this often, so let me figure out exactly where they live. Okay. All right. So under transform and morph, we want box morph. All right. So we've got box morph. Then we need to reference in the geometry as a tile. So that's under surface, primitive, bounding box. So bounding box is going to create a 3-dimensional domain around a geometry that we reference into it. So let's take a look at our connections. Bounding box can have a generic geometry input, and you can locate it based on a plane. Okay, so we are only concerned with just putting the geometry on the tile, or putting the tile on the geometry. Sorry. So I'm going to go into params, geometry. Oh, you know what? Sorry. Here we go. This is under surface, primitive. I'm going to go under params, under geometry, and grab a geometry input. And with that geometry input, I'm going to set it to the extrusion that I just created.
How much are we extruding it by?
I just made it a foot. It doesn't really matter though,
Okay.
and you'll see why. So the geometry gets plugged into the geometry input, obviously, and this is what it does. It creates a domain around it. So now let's take a look at the morph inputs. The morph input is asking for a geometry. It's asking for a reference box, right? So our output here is a box. And it's asking for a target box. So that kind of tells you the relationship of these 3 things. It needs the original geometry. That would be the geometry that we just linked in. You guys keeping up?
Not yet.
All right, should I pause here? Are you guys? All right, so I'm going to pause here. I want to see you guys get to the surface box first before I move on. And then if you can get these 3 laid out, that'll set us up well to move on forward. So here, we're almost there. It's actually really simple at this point. We can simply plug in the box to the reference, and then we need to plug in for the target box, we plug in the surface box, and it'll take a while to compute. But what you wind up with is a tiled surface across your whole model. So let me start turning a few things off so you can really see what's going on. Well, I'll turn that off too. So this is what you'll wind up with, everyone. If you do it right, you'll wind up with this.
Oh, well, there's the catch.
Yeah, that is the catch.
Can we turn off Geo?
And also, if you go back to your extruded floors,
Oh, that's rad. Which one's the extruded floors?
that's this right here, the extrude that's all the way down there.
Oh, okay.
Yeah. So notice here that it actually set a direction for the tile. So yes, you can change it. That's a good question. You can change it. What you have to do is you have to rotate the actual geometry. So it's kind of weird there, but all you have to do is select the geometry, rotate it 90 degrees, and oh, look at that. Oh, it's computing. There we go. See? So it's referential to the X and Y direction.
Wait, how do you change the direction again?
You just rotate the geometry.
Oh, that original box?
Yep.
Oh, cool.
Okay. So yes.
So how do you make it like, because you know how the pattern's above or like surpassing the actual tower? How do you
think this would be
how do you make it? Yeah, because mine says like not.
Oh, right. The truncation is what you're talking about, right? All right. So that's a good question. If you want to truncate the pattern, you then need to feed it back into the same system that you were doing with, I guess it would be surface difference. So we had our joined. Yeah. So you could plug it back into a surface difference. I would probably just copy and paste and replace the link. So this one is being plugged into the top. So you replace that with your new geometry, and let's see if that works.
What is truncating?
Truncate means to cut off the top
Oh.
at an oblique angle. So it looks like my original, if you look at my original geometry, it's not, whoops.
Oh.
No objects are hidden. Oh, that's why. I was looking at the backside of my box. Yeah, so let's see. Why didn't that work?
Is it not going through all the way?
Isn't it just doing the bottom?
Do I want it to trim instead? It's doing a surface difference. Oh, I know why. All right, so this one's a little bit different because every single one of these B reps are reading as an individual surface. So when you do a surface difference, it'll trim out the ones that engage, but you need to figure out which ones are actually inside of the box volume to get rid of the rest. And that would be these, right? So notice how it trims the ones that are intersecting, but then the ones that are inside of it are still they're still a full panel. It's not just split. So we would have to, there's a process for that. You can actually measure which ones are inside of a volume, and I can show you that at a certain point. I think it makes sense to show you that now. But I'll have to prepare for that next week, I think. Yes?
Does it only work with when it's a flat surface, or
Eliminating these?
no? Like creating the paneling and stuff. Does it only work on those flat surfaces?
No, this is a warped surface. See?
What's the B input for, what's that called? Solid difference connected to? Oh, here?
This is connected back to the B-rep, which is this cube. Okay. Actually, I could try and figure that out, but give me a sec to play around with it, and I don't want to get, I don't want to get you guys all turned around. So give me a sec to play around with that while you guys are messing with this, and then I'll try to get it in the video for you.